Welcome to Heterogeneous University. My name is Quentin Oshem, and today I will be presenting the basics of record types. Let's get started. Back to the type chart. We saw arrays in the previous presentation. We are now going to talk about a second type of composite data structure, record, which is going to allow us to create heterogeneous data structures. A record is the equivalent of a C structure. It's a type in Ada that starts with the reserved word record and then is followed by a list of components declarations. As you can see on this example, those components look a lot like variables, although there are some specific restrictions in what can be done here. Once such a type has been declared, it can be used to type variables or parameters or even other components. In this example here, I created a variable s of type shape, and I can then access to the component of shape through the dot notation. Here, for example, s.x gives me access to the x component of s, and I'm assigning this component to 0. s.id gives me access to the id component of s, and what I'm doing here is assigning it to 1. It is possible to use another composite data structure to type a component within a record. So in this example here, shape contains two fields, name and p. Name is an array, it's actually a string constrained between 1 and 10, and p is an instance of position, which itself is a different record declared earlier. One important point is that, as with array components, record components need to be of a fixed size type, of a definite type. And as with arrays, the actual size may only be known at elaboration time, as it is shown in this second example, where the length of name type is initialized after a variable which is itself initialized after a subprogram call. However, such structures have an impact on the efficiency of the code generated, so it's advised to always use component types that have a size known at compile time. It is possible to provide a default value for a component within a record. As a matter of fact, this is more than a value, it is really an expression that is going to be used to initialize the value of the component in the absence of any explicit initialization. The fact that it's an expression is important because this means that it will be recomputed each time an object is created. In other words, if I take the second example on the screen, x and y are computed after the value cx and cy, which are variables. These variables equal to 0 at the start of the program, and if I declare a variable of type position at that point, the value x and y will be equal to the current value cx and cy, so 0 and 0. Later on, I can change the value of those two variables, cx, cy, and set them to 1, for example. And if I create a new instance of position, p2, in this example, the initialization expressions are going to be recomputed, re-evaluated, and this time the values for these p2 objects are going to be 1 and 1. As with arrays, there is a literal for records which is called aggregate again. The syntax is quite similar to the array syntax. It's opening a parenthesis and then listing values one by one. The first syntax that is shown here is the positional syntax. So value have to be given in order. It is possible to use name notation as well, and it's actually possible to mix the positional notation and the name notation. The one restriction of this way of working is that you need to start with the positional notation, and once you switch to providing names to the fields, then you cannot go back to positional notation. Note that these aggregates can be nested one within the other. For example, here when I'm initializing circle, I'm opening a first aggregate, and then I'm opening a second aggregate to actually initialize the string, which is an array of character. And then for the second value, I'm just reusing the value coming from a previous initialization through the center variable. A couple of interesting things to know about aggregates. First of all, when the aggregate contains only one element, such as one variable, the positional notation is illegal. It has to be done through a name notation. The reason for that is some corner cases in the syntax of the language where the positional notation would not allow to differentiate a conversion or an aggregate. Another interesting feature is the others box. What this says is that for all the remaining components of the record that have not yet been specified by the aggregate, use the default values. So in this case, E1 is initialized by an aggregate which says only use the default values. Arguably, this is not very interesting here because I would have taken the default values anyway. But if I want to provide values for some object and not others, that can get quite handy. On V2, I'm taking more advantage of this notation. I'm saying that A equals to 0. Actually, I want to specifically say that for the value of B, I'm taking the default, and all other components will take the default values as well. Note that in this very case, the type rec, which contains A, B, C, D as integer, does not specify any default initialization expression. So in this very case, default would be whatever is in memory at this very time. One last feature. If all the remaining components are of the same type, it is possible to use the others notation to provide the same expression, the same value, for all of these remaining components. Which is what I'm doing on this last example here. I'm providing a value for A and B through the positional notation, and then I know that the remaining components are of type float, and I'm saying that all of these others components will receive the value of 0.0. Let's now talk about discriminants. In certain situations, the same type needs to be used in different situations, and depending on the situation, some components may be used and some other component might not. Taking this shape example, there are 6 components which will describe shapes on the screen, and mainly a line, a circle, maybe a torus. But all of these fields will not be necessary in all situations. For example, if I define a line, I will need x, y, and x2 and y2, and that will be enough. If I define a circle, I will need x, y, and radius, and that's it. So depending on the situation, I'm going to reserve extra data that is not going to be used. It's actually even worse than that. If an instance of shape is aimed at being used as a line, then radius and outer radius should not be used. So not only am I using extra memory, but by allowing people to use those fields, I'm letting them making mistakes. So let's see how we can improve the situation here. It is possible to create a parametric type, a type with discriminant, saying that the component of the type will vary depending on the value of this discriminant. In Ada, this discriminant has to be a discrete type. There is a special case for access type that we will describe a lot later, but for now let's focus on discrete types. In this example, there is a discrete type that I introduced in the program, which is called shapeKind, which can be circle, line, and torus. I am using this enumeration to create a discriminant kind of shape. So in this example here, straight after the record wizard word, I am introducing the components that are going to be common to all the possible forms of shape, to all the possible values for the discriminant. In this case, x and y need to be shared by all instances. I'm then introducing a case statement, saying that depending on kind, here are the extra components provided. If the discriminant is of type line, then I'm going to add x2 and y2. If it's torus, I'm going to provide outer radius and inner radius. And if it is circle, I'm going to provide just radius. An important point here, as soon as I add the discriminant to a record definition, I am creating an indefinite type, a bit like an unconstrained array. So at object declaration, I will have to specify the discriminant. I will have to specify which form of the shape I want to create here. For example, when I write v type shape with the value circle, I am creating an instance of shape of the form circle, which will contain x, y, and radius as components. Now you might be wondering why in torus I didn't have something like radius and inner radius. So why did I need to create a new name? The reason for that is that even if they are in other branches of the case statement, every component needs to have a unique name. So I cannot have the same name that is replicated into two different branches. In terms of check and initialization, you will find similar rules as you had with arrays. In particular, if the discriminant is not provided by the variable declaration, it can still be extracted from an initialization. So in this example here, v2 is of type shape, and I am not providing a value for the discriminant. However, there is an initialization, so the actual value for the discriminant of v2 will be the one of its initialization v1. Once this is done, the compiler will add checks so that it makes sure that I'm only accessing two pieces of data, two components that are valid. v1 being a circle, I can access to radius and modify it. However, x2 is not available for circles, it's only available for lines. So if I try to access to x2 of v2, I will get a constraint error. As a matter of fact, the compiler will not even generate the memory to retrieve this component. So in this example, there is no x2 at all in the instance v2, and the compiler checks that I'm not trying to access to something that does not exist. Of course, the value of this discriminant have to be constant. It's a bit like an array boundary that doesn't change as soon as the array is created. So any attempt to modifying the value of a discriminant will issue a compilation error. However, the same value can be accessed in read mode if required. From the aggregate point of view, a discriminant is just one of the fields that have to be specified in the list of fields. All the usual rules will apply with regards to the positional and name notation in particular. And of course, the list of fields that have to be provided depend on the value of the discriminant. So for example here, if I'm saying that the kind is line, the aggregate is expected to provide the value for x, y, x2, and y2. If the discriminant is circle, only 3 values are expected, one for x, one for y, and one for radius. Let's now move to the quiz section of this presentation. For this question and the next, look at the code below and try to identify errors. If you think that there is no mistake, you can click on the green icon next to the yes and then hit submit. If you think there are mistakes, then click on those in the code and then hit submit. As with arrays, record aggregates need to describe completely the structure they're providing a value to. Here, R is a record of 3 components, A, B, and C. But in the aggregate, I am only providing a value for A. So the aggregate is not complete. This will be a compilation error. I could complete the aggregate by the others box notation, for example, or by providing an explicit value to B and C. This is a bit confusing, but it's very important, again, to understand the notion of strongly typed language. And remember that the others with a value can be used only if all the components are of the same type. So here, A, B, C are of type integer. D is of type myInteger. So those two types are different. Although they could all be initialized with the same expression, the literal 1, it is going to be refused by the compiler because the rule is clear. It says that all the remaining components have to be in the same type to be able to use this notation. And here, D is a different type than A, B, and C. This is a common mistake when coming from reference-based languages such as Java, Python. A record type cannot be recursive in Ada, at least not without using a reference-like structure, like a pointer, which we will see later. But right here, what I'm trying to say is that a cell contains a cell, which itself contains a cell, which itself contains a cell, etc., etc., etc. So you can see that this structure is of an infinite size because of the recursion. This will be detected at compile time, and the compiler will refuse to compile the structure. This is perfectly fine. When I'm saying others arrow box, what I'm saying is that all the remaining components, or all the components in this case, will take their default value. There is no requirement for those components to be of the same type. Now, in this very case, what's interesting is that there is no explicit default values for these components. So we cannot make any claim on the content of V at this stage. Whatever information is in the memory at the point of declaration will be taken and used as value for the components. Remember that when there is only one component in a record, the positional notation is not allowed in the aggregate. So I need to use a name notation here, A arrow 0. Again, that same frustrating side effect of not using a reference-based language, but a stack-based language, is the fact that in composite data structures, arrays, or records, I can only have components that are definite, that are fixed size. Here, I would like to have a string as a component of my record R, but this string is indefinite. I do not know the size at this stage, so that will be refused by the compiler. In this example, I'm trying to work around the need for having a string of a fixed size by actually providing a size at the record declaration time, which is fine, this is working out. However, it means that the string needs to be of 10 character. In the aggregate here, I'm only providing 5 character through the hello chain. So this will be refused at least at runtime, and in this very case probably at compile time as well, because the compiler will be able to do the analysis, verifying that there's a mismatch in terms of size. One quick word of explanation on this one. We haven't seen that in the slides, but to create a record that does not contain any components, I need to tell the compiler that this is expected to have an empty component list. It's a bit like sequence of statements that can't really be empty. So if I want an empty component list, I need to say that explicitly by providing a null component. Now, having said that, do you think that this piece of code is correct? Remember, a discriminant is constant. So if I was allowed to assign v2 into v1, I would change the discriminant. I would change the structure of the object. Now, in this case, the structure is physically the same. It's just a record which contains a constant, which is an integer. So, from the technical point of view, at the lower level, I could completely provide an operation that does this assignment. But at the semantic level, at the logical level, this assignment is forbidden because those two objects are logically, structurally different. One has 5 for the value of the discriminant d, and another one has 6. And it could be the case that those two objects have a different set of fields, but Ada does not quite care about this fact. It just follows the rules that two objects with different discriminants cannot be assigned one to the other. That will issue a constraint error. The constraint here is that within a record, the component names need to be unique, even if they are in different branches of a case statement. So here, x and y are declared a first time in the line case, and then a second time in the circle case, which is incorrect. I should use unique names here. Now, of course, in this very situation, the proper fix would be to extract X and Y and put them in the command part of the record. Discriminant needs to be constant. They should really be viewed as the equivalent of boundaries for array. It makes sense that they cannot be changed. Here, v.kind is the discriminant of shape, and I'm trying to modify it to assign line to it. That is a compilation error. This wraps up this first introduction to records. As a matter of fact, we just scratched the surface here. There is much more to come about records. Stay tuned.